to John, G4BAO. What makes the pings go ping?
Thank you. Can you all hear me at the back?
No.
Dave, can you hear me? Good. Right, well, first of all, I apologise for pretending not to be a microwaver this session, so I'm going to talk about something somewhat lower. So, this all goes back about 30 years. My interest in meteor scatter as a hobby goes back about 30 years. My interest in meteor scatter as a hobby goes back about 40 years, but about 31 years ago now, I was working in the labs at Pi, and I was allocated a very clever young man whose name was Chris Rycroft, who was G4FES at the time, and he was doing an undergraduate program at Plymouth Poly, and his research project was a thing called endpoint scatter, which is to do with meteor burst and antenna geometries. And he covered it like you would in an undergraduate text, fairly loosely, and didn't do much. And this fascinated me. I got talking to him. And to cut a long story short, that then became a 6-year research project for me. With Chris's permission, I took up his topic and turned it into a PhD. So that's how I got interested in this. This is not how to do meteor scatter on amateur bands. We had that from Lynn about 2 years ago, and John rang me up and said, would you add some more meat to what Lynn had done? So I'm going to present you with some information that might help you understand a little bit more of what's going on. I promise you the terrifying mathematics behind this will be hidden, but I hope to point out some of the interesting things that come out of it. So I've called it What Makes the Pings Go Ping, because I couldn't think of a better title. So that's a bit of history of me, but the history of meteor scatter goes back a long way. You might think it's fairly new, but the first, I've just got a list here of in the history section of some of the stuff that has gone on in the past, but roughly what I'm going to cover some of the principles behind meteor scatter, how meteor trails are formed, difference between shower and random meteors, the types of meteor trail, because there's more than one, what happens with frequency, and the thing that I was particularly interested in, what happens with the path geometry, and what determines system throughput on a meteor burst system. I shall mix the terms meteor burst and meteor scatter. You can always tell the professionals because they will call it meteor burst, whereas we call it meteor scatter, but it's exactly the same thing. So I'm also going to cover right at the end, and John's going to go into this in quite a bit more detail, I think, in his talk, some of the system issues with meteor scatter, some of the myths, some of the things that you'll hit upon working meteor scatter from a nice suburban location like mine. And it's really down to antennas and receiver performance. So, some of the history. Believe it or not, the first ever paper on meteor scatter came from Japan in 1929. And it was from the Proceedings of the Imperial Academy of Tokyo, and it was wonderfully translated Japanese, the possibility of radio transmissions being disturbed by meteoric showers. So this all came about, people looking at the effects of meteors, the negative effect of meteors. And this guy with the best name in the world, this is a fantastic name. This guy has to be American with a name like Greenleaf W. Pickard, doesn't he? So he then 3 years after the Japanese came up with that. But again, this is all to do with the effects of meteor showers on radio reception rather than using it as a communications medium. So, and then it was then there was something happened between 31 and 48, I can never remember, something important. And then Bernard Lovell and his partner, Mr. Clegg, started to look at a radio astronomy perspective on meteors. Oh, there's always one, isn't there? Go on, I'll just wait till it goes really red, and then I'll carry on. So the first real scientific study into meteor scatter was in 48, just after the war. Lovell came out of his radar work during the war, and they started looking at radio echoes from meteor trails. And you can see how it's progressed. 6 years later, they were starting to think about actual communications via meteor scatter. And this is the classic paper on meteor scatter. If you're going to start learning a bit more about the details of meteor scatter, it's Eshelman and Manning. And then in 1957, the first commercial meteor scatter system came on board, and it was called Janet. And it had certain advantages that the Khaki Trousers Brigade liked. It worked in the Arctic. The only thing that stopped it working was a nuclear attack that took out the ionosphere, and who cares after that? It's incredibly reliable as a communication system, and this Janet system was probably the first serious system that used meteor scatter. So there's a whole raft of work on this, goes right back to 1929, and then it then started to accelerate in the 1980s with digital communication techniques. Meteor burst modems became de rigueur, really, everybody had them, and it was used for remote data gathering from awkward places like the Arctic. So that's a sort of historical background to all this. So, moving on into a bit of the theory. So I'm going to try and help you understand the signal characteristics of meteor burst. You've all heard bursts and pings and things like that. So why is it like that, and what happens when you change things? So, the first thing to get across is we're not talking about meteorites here. We're talking about particles, tiny particles, and there are millions of these particles being swept up by the Earth as it goes around the sun. So it's there all the time. It isn't just showers. The commercial systems work 24/7, and they rely on the fact that there's so many meteors. It's meteoric dust, is for want of a better phrase. Most of these particles burn up in the E region, and they never reach the ground. When they reach the ground, it becomes a meteorite. But what we're talking about here are just small particles, and they vary in mass from 0.1 of a microgram to 10 kilograms. They're the ones we're interested in. Anything less than 0.1 of a microgram just goes through the atmosphere. And anything bigger than that is so rare as to be not really of much interest. So we're talking about particles between the size of a grain of sugar to the size of 5 bags of sugar. Okay? That'll give you the range that you as communication people are interested in. And size is from a couple of hundred microns to 80 millimeters. So it really is meteoric dust. The other thing that's interested in this as well, and again, this explains quite a few things that happen in communications, the mass distribution of this dust is almost exactly such that there's approximately the same total mass of each size of particle. Yeah? So, what that means is, if I can get the thing to move, hang on.
Use the forward and reverse arrows.
Yeah, so what that means is that there are 10 times the number of 0.1 microgram particles as there are 1 microgram particles, etc. Yeah? So the sort of mass distribution is such that the big ones become very, very rare, and there's lots of small ones. And it's roughly that relationship. There's about the same total amount of mass per day. So there's 1,000 kilograms of 0.1s a day, and there's 1,000 kilograms of ones a day. That's just a figure I pulled off the top of my head. So you can see we are talking quite small particles here. So the first thing you must realise is this is not reflections from meteors. This is reflections from the trails that they leave behind. Because anything down at 0.1 micrograms, radar cross-sectional, will be tiny. So it's meteor trails. Terms of velocity, these figures are reasonably close. Anything between 11 and 72 kilometers per second. Anything that's going too fast is at the escape velocity, so it never actually gets to Earth. Anything that's too slow just doesn't just doesn't get swept up. So their velocity is also governed by basically escape velocity. Anything that's going fast will just go horizontal and will never get to the Earth. So, types of meteors. I'm only really going to talk about random meteors today because all the equations I'm going to throw up very quickly, I hasten to add, are related to random meteors. Shower meteors are the ones that we have a lot of our DXQSOs using because there's a huge increase in the meteor flux when there's a shower, so there's more of them. They're still the same sort of size, but they're basically remnants of comet tails. And I was earwig in a conversation with one of the astronomy guys, and they're trying to collect information on the sort of radiance of these meteors, so they can try and relate them to known comets. And there's quite a bit of work going on that apparently in the radio astronomers. So shower meteors, they're well known and predictable. They intersect with the Earth's orbit at the same time every year, roughly, give or take a few hours. So we all know that January has the quadrantid shower, and we have the Geminids in December. Is that right? Yes. And the reason they've got these esoteric names is that's the constellation from where the radiant is. So what we're talking about here with showers is, in simple terms, it's a point source of meteors that are coming towards us. So we can predict where the radiant is. From that you can work out the path geometry, and you can then work out the best directions at a time of day, and you can beam in the right direction. And all these websites and programs you can buy work on these fixed meteor radiants. And these radiants rise and set in the same way as the planets do. So this is why you don't get meteor scatter contacts at certain times of day, unless the radiant's circumpolar. In there you'll see it at 24 hours a day. So they radiate from a fixed point in the sky. And also, you look at the photographs that people take of meteors, you can very clearly see that they all do this. If you point it towards the radiant, they radiate outwards and spread out. So, point source. That makes the calculations a little bit easier, actually, if you know where they're all coming from. So, as far as the professionals are concerned, the people who do design meteor burst modems, they're not really very important, because they're relatively infrequent. There's just a few showers a year, and they only provide short-term enhancements. Okay, so during a shower they can get more throughput. Just as an aside, these meteor burst modems, the automatic ones, most of them transmit a probe signal, and they sit there waiting at the other end until it hears the probe signal. Once the modem at the far end hears a probe signal, it sends a signal back on the same meter and says, "Send me all your data now," and it sends it back until the probe signal disappears again. So you can work out protocols, and one of the guys I spoke to when I started my project was an expert on these protocols, and there are certain optimum ways that you can make these modems work. So it's not like we use meteor scatter. These things are 24/7 systems, and they only transmit the data when there's a meteor there. And that makes sense, because you can get as much across as you can. So I'm diverting slightly, but shower meteors are of less... Hang on, bear with me a second. No, it doesn't like pressing that one, does it?
That is not a good escape.
That'll close it down, won't it? Oh, no, it doesn't. Sorry. Okay.
Choose the arrows.
What is it they say about? Yeah. Okay, random meteors. This is what I'm going to really talk about now. This is the sort of thing where you can go on the air any time of day, outside a shower, and work meteor scatter. Because remember, there are millions of these particles every day. They're not all usable, but there's always something to work. They're far more numerous. There's thousands of these, millions of these a day, and they occur all the year round. As we'll see later, there's a slight variation throughout the day and throughout the year. But generally they work all the year round. And they travel around the sun with no particular orbit, unlike a comet. But the majority of useful ones travel around the plane of the ecliptic, which is the Earth's orbital path. Okay, so you've got the Earth going around the sun like that, and you've got these meteors in the same sort of area, and they'll intersect. Anything that intersects with the Earth's orbit and is going fast enough, but not too fast, will cause a trail. So, what you get, and I think anybody who's worked meteor scatter, what's the best time of day to work meteor scatter?
Early morning.
Early morning, right? There's a very simple reason for that. Because what you actually get is you get this diurnal variation, the daily variation. It gives a peak at around 0600 local at the path midpoint and a minimum at 6 o'clock. Now, if you remember what I've just said about where the meteors are coming from, the morning, because if the Earth's travelling that way in its orbit, and the Earth's rotating that way, what you're going to get in the morning is that the relative velocity of the meteors and the Earth is bigger because it's going around the sun plus it's rotating, so you get the rotational velocity plus the orbital velocity. So simple as that. The Earth sweeps up more meteors in the morning, whereas when you get to the evening, it's rotating away from the main meteor flux, and anything that comes into the Earth's atmosphere has got to be travelling faster than the Earth. So you get this roughly sinusoidal variation in meteor flux during the day. So that's the first thing that the physics has explained today. It's explained why we get these morning things, get these morning peaks. Okay, so in the morning, the two rotations add together relative to where you are on the Earth. In the evening, they subtract, so you sweep up fewer meteors and they're slower. Okay, so next time somebody asks you why, you can explain it. I should really have drawn a rotation arrow on there, but it doesn't matter. Okay, all with me so far? Good. There's also seasonal variation. As you might imagine, because of gravity, the meteors tend to clump together. So they're not uniformly distributed around the Earth's orbit. They clump together. Anything with any mass will tend to go towards another thing with mass. So you end up getting clumps of meteors. And though effectively the clumps are predictable, where's my graph gone? There should have been. It must be a colour that John's PC doesn't support. But you get the idea. What you get throughout the year is you get a minimum of meteors, random meteors, in February, and you get a maximum in midsummer. And these points here, these are all the showers. So as you can see, February is the worst period of the year for meteor scatter. There's no showers. The random flux is actually at its minimum. So February is a good time to get your antennas down and fix them. So it peaks around mid-July, and it's a minimum in February. So you've got a daily variation of the Earth's rotation, and you've got an annual variation because the crap that's rotating the Earth has clumped over the years. So you get this seasonal variation. I would imagine in the long term that'll sort of start to move and change, but probably over time beyond us. So, meteor trails. I went right back to the start and I said it's not the meteors they bounce off, it's the trails they leave behind. So you've got these high energy lumps of rock, dust, water, all sorts. They hit the air molecules. They've got enough energy into the air molecules to strip off electrons from the air molecules, and they leave behind them a trail of ionized particles. It's mainly metal ions because there's a lot of metal in meteoric particles, and free electrons. So if you've got a cloud of free electrons, you all know what happens. It's like the F layers and the E layers. It bends radio waves. So what you end up is with a long, thin paraboloid, you know, the classic comet shape of ionization with the meteor at the head. And of course, as soon as the free electrons are out, all the other ions try to recombine with the electrons. So what you end up with is you get this trail, and it slowly recombines, and you end up with unionized air again. So what you get is a signal that, or you get ionization that goes up and then decays. Okay, and you end up with a short-lived reflecting or scattering medium for HF, and whether it's reflecting or scattering depends on how many free ions and free electrons you've got. And that measure of ionization we'll see later is called electron line density. And that's basically to do with how big the particle was. The bigger the particle, the harder it hits everything, and the more ions, the more air molecules it hits, so it generates more free electrons. And of course, also, the denser the atmosphere, the more chance the electrons have to recombine. And the higher up you go, they'll take longer to recombine. So what you get is a reflecting layer, effectively. And it's roughly 100 kilometers like the E layer. So the sort of propagation distance you get through the E are the same as for things like sporadic E. So we've seen the types of meteor, the sporadic and random meteors. There's different types of meteor trail. And they do react in a different way. There's what we call pings. The professionals usually refer to as an underdense trail, and I think you can see by the name that's going to have fewer free electrons than the other type. And the big thing about that is the electron density is low enough so that most of the energy goes straight through it. Some of it's scattered off in all directions. So with underdense trails, it's definitely a scattering rather than a reflection. Okay. The other type is overdense or bursts. These are trails when the electron density is high enough for the trail to act as a highly reflecting surface. So if you've got an overdense trail, you get this total internal refraction, the same as you have with HF and the F layer, and all the energy comes back as a specular reflection. Angle of incidence and refraction the same. Okay? So, two different sorts. And what we're going to do, we're going to sort of drill down into this idea and just see what sort of signal shapes you get and why they're that shape. Because what you find is once you echo a signal from that, the return signal has a specific shape. Underdense trails generally have a very, very fast rise time, a slowish decay, and they last a few tenths of a second. So I think you can see what's happening. At the real high energy end, the free electrons are formed very quickly, and they diffuse and recombine. So that's and you can see these. If you use WSJT on FSK 441, you can see these shapes quite clearly on the graphs, and you can say, that's an underdense or that's an overdense, because an overdense is much, much longer. It starts relatively slowly, and it lasts longer, and it decays. So it's a completely different shape, and you're talking about a number of seconds rather than a few tenths of a second. So, and this is all down to particle size, basically down to particle mass. The small trails generate a small amount of free electrons, and they recombine. But here you end up with a complete cylinder of reflection that lasts a long time. So again, next time you're doing meteor scatter, have a look on the WSG JT graph scales, and you quite clearly see the big bursts generally look like that, and the small bursts look like that. Or at my site, because my noise levels are there, they look like that. Unfortunately, which is why I don't do meteor scatter very often anymore. Right, I love this word. The path geometry requirements are that the transmit and the receiver are at the focus points of a prolate spheroid. It sounds like something 60-year-olds go to the doctor about, but it's not. A prolate spheroid is an ellipse in 3 dimensions, a rugby ball. Yeah. So if you can imagine half a rugby ball, the trail, the transmit and the receiver have to be at the focus of that, and you have to have specular reflection here, angle of incidence and reflection the same. So that really ties the geometry down of this path. And this explains why, apart from the fact that he's got a bigger antenna than me, he'll see different bursts from me, completely different bursts, because he'll be looking at different different reflections. And one of the consequences of this is that the reception area from a meteor trail that it puts on the ground is boomerang shaped. And if you do a bit of geometry, you can work that out fairly quickly and see what shape it does. So if you're in a different part of if you're not within that boomerang shape, you won't see the same burst as your mate 3 miles away, and it can be as close as that because it's right down to the wavelength as it works. So imagine your transmitter, the focus, a trail in the right direction, you will get a reflection. And the reason you get lots of reflections is lots of meteors. And this path criteria, this is what the military love, because it makes it impossible, almost impossible to jam, because you have to be at the same point to generate a jammer. So the military love this, because it's completely uncorrelated on 2 sites that can be a few tens of miles apart, if that. Okay? So looking down on the top of that, this is looking down on the Earth's surface, right? So this is looking down from above. We've got a transmit and receiver here. You've all seen hot A and hot B on the WSJT thing that says point your antenna slightly off the Great Circle path to work the best. Well, the reason for this is once somebody points it out to you, it's really obvious. If you're going to go down the Great Circle, the only trails that meet that requirement for specular reflection and to be on that prolate spheroid are travelling parallel to the Earth's surface, which means they're at escape velocity. So there are hardly any trails like that because that 72 kilometers per second generally doesn't get you up to the escape velocity. So trails like that and anything in between down the Great Circle distance are very, very unlikely indeed. What does happen is you get trails. Here's our rugby ball. They're falling towards the Earth. So what you get is trails going down the side of this rugby ball. I should have brought a rugby ball with me, shouldn't I? So if that's just use your imagination. That's a rugby ball. So trails like that are fairly unlikely, but ones coming down like that are very likely. So you can see straight away that if you're going to see trails like that, you're going to have to beam slightly offset to meet this specular reflection criteria. So what you get are hotspots, and those hotspots vary between the day and the night. I won't go into the details, but basically, I can never remember which. It's slightly south of the Great Circle path. Is that in the morning or the afternoon? I can't remember. And it's north the other time anyway. It does vary throughout the day. So what you're doing is reflecting off trails that are doing that. So can anybody work out what the effect on the signal just of that geometry? Think of a mirror. Hold a bathroom mirror up at 45 degrees and look at something through it. It's not vertical anymore, or it's not horizontal anymore, is it? What you get is a fixed polarization tilt, but nothing more. Purely depending on what angle your mirror is, you'll get a very slight polarization tilt, and that's calculable. What you don't get is random polarization. I've heard so many people say, "Oh, I'm going to use vertical polarization today," and you think, no, well, but it's a calculable polarization shift. Okay, so if you have so this is why the fixed meteor burst boys who are doing just one point-to-point path, they can tailor the polarization of their antennas to suit the path exactly, or to suit it statistically, should we say, because it won't be the same all the time. So, but what we do get and we do see is these two spots. You effectively get two hot spots. So it's down on the path, and you have to beam slightly off the grid. Hey, I've done this without maths so far, haven't we? I've explained most of it. We're doing well. But it is all about geometry. Whoops. I've just put these up. These are just two. This is looking down on the path from above. You've got transverse and inline trails, and this angle becomes important fairly soon. And you've got, so you're looking down on the path. Basically, you're going to go off to one side and back. Off to one side and back. It's a path slightly. And then looking at the side, you're going to go up to the ionosphere, somewhere up at the edge of this sloping rugby ball, and you're going to reflect back down. So I'll refer to these angles. That determines the path length. The longer the path, the bigger the angle has to be. And so that's the sort of geometry that's involved in this. Frequency, another classic paper by George R. Sugar, radio propagation by reflection from meteorites. I think this was the first one who defined this transmission wavelength. Something happens above a certain frequency where all the equations change. And George R. Sugar pointed this out. And he said, at long wavelengths, and this is why, and the formation, that's the rise bit I talked about, is negligibly small compared to the long total decay. Yeah? It doesn't change because that's the time it takes to get ionized. But what happens is the duration in a transient state tends to remain constant. But the decay, and once the wavelengths get short enough, only the transient state's left, right? Okay, so you've got this transition frequency, and it's around 91 megahertz. It's about 3.1 meters, and there's about a whole 2 papers full of maths behind that. And please don't ask me questions on it because I don't understand. I know Marcus is looking. He's looking puzzled. He looks like he's going to ask me a question. Well, don't, because I can't answer that. I'm going back. But this is what happens. Everything changes above about 91 megahertz. So people talk about transition or transition frequency, and I love this. Simplified path equations, right? I've skipped 3 pages of derivation here, and this is the simple case. This is received power at long wavelengths from an underdense trail, assuming a uniform radiant of meteor, a uniform distribution of meteor radiance. I'll leave it as an exercise for the student to work out the actual. This is very good because it points out a few certain things about it. You've got a huge great constant term, which is your radar equation, PT, GT, GR, radius, and so on. Right? So that bit you recognise. And you've got a double exponential decay, e to the minus and e to the minus, right? So that's your decay. So, the interesting things it points out, the path loss for long wavelengths, or in our case, 50 megs, under dense trail, the path is proportional to the frequency cubed. In frequency, the loss goes up by a power of 3. So it's quite, this is why the reports of meteor burst at 77s and above are so. There's your exponential decay term. This is your under dense shape. Just worry that it's e to the minus, that's all you need. And it's got a polarization term. Alpha is the angle between the trail and the polarization. Okay? And the rest of it's the radar equation and a bit to do with path length. That one down there is the initial trail radius. Because there's a sort of initial trail. That happens very quickly. And you get a small radius of trail. So that's the horrible maths. As I say, there's 3 pages of derivation behind that. I have done it 30 years ago and I've forgotten most of it. You think that's difficult? This is for short wavelength underdense. And that is multiplied by that lot. So I couldn't even fit it on the slide. This, again, it's a simplified case, but this is short. This is 2 meters with underdense trails. But don't panic, because there are things in there that we recognise. We've got the same polarization term in there. Shift. So it's the same. This time the path loss is proportional to the 6th power of wavelength. So this is why you work it on 2 meters, and when you get to 23 sems, unless you've got a 10 meter dish like Zdenek, you don't work meter scatter on 23 sems. It's a frequency to the power 6th law. Yeah, so double the frequency and you get 2 to the 6th power. But hidden behind all the maths, and this is an interesting one. This one always fascinated me. Do you remember that angle phi was the angle between the trail and the vertical to the meteor? This sine squared alpha term tells you that the longer the path is, the less loss you get. But if you take that to an extreme and have alpha equals 90 degrees, you've got line of sight, haven't you? So that's not too difficult to sink in, is it? So that's the horrible equations. I promise we've only got one more. This is the duration equation. This is much simpler. For some reason, they define the trail duration as the time to fall of 1 over e of its value, which is 8.7 dB. Why they didn't just use 10 dB, I have no idea. But you know what these academics are like. So the duration term, that's the burst length, obviously to do with our diffusion coefficient. That's how quickly the trail recombines and spreads out. And it's and that one's inverse, and that one's a frequency squared law. So as you go up in frequency, the trails get weaker and they get shorter. And you've all seen this. The difference between 2 and 6 is quite obvious. But this thing's here again in the duration term. You've got this 1 over cos squared phi thing. That means the longer the path, a large phi, you get a longer duration. So the extreme long paths are long duration. And if you want to take the short wavelength case, it's a completely different definition of duration. But in arithmetical terms, it's about 0.633 of that value. So again, shorter bursts on the short wavelength cases. But believe me, those things are, yes. Oh crikey! Right, moving swiftly along. Right, let's move on to system issues. I like this photo. That's a pinned 500 watt through line. John just went 500 watts when I did that. But life's too short for QRP. So if you want to make meteor scatter sing, you've got to run high power. But the big key to success is your antenna and its environment. That's the old HP9Q EMI system. And the things that really matter: the antenna and its elevation, and the noise levels you've got on your site. And that last one is the real killer. Takeoff angle. Like on HF, if you're going to work the extreme distances, you want a very, very low takeoff angle. And if you look at this from G2WS's wonderful paper with a wonderful title of Zen and the Art of Stacking, The problem is, as you move the distance out here, the takeoff angle drops. Okay, so and the arrival angle of the signal. So if you're going to work the extreme distances, you need to be at very, very low elevations. So here's a picture of my 6 meter antenna. This is a bad 50 megahertz DX antenna because it's only length above ground. It's really impressive. It frightens the hell out of my neighbours when I put it up. But it's only just above chimney level, and it's a rotten antenna for two reasons. One, it's too low, and two, it overhangs the house, which is full of horrible things that generate noise. So I don't do much sensible meteor scatter. I'll go on when there's a...
Probably 70 megs as well.
Yeah, but one of the things, if you look at this is a 6-element Yagi at one wavelength above ground, so that's just a little bit lower than mine. First of all, it's got two main this is a vertical H-plane thing. The main lobe is 15 degrees above horizontal, and the second lobe is 45 degrees above horizontal, and you've got similar things at the back. So your incredibly expensive 6-element Yagi, unless you put it up a real number of wavelengths in the air, is going to point upwards. So don't be surprised if you only you don't work the extreme distances that John does with his carefully tailored antenna. So that's the first thing to remember. 6 meters is quite a hard band to do meteor scatter on. For 144 meg, Joe Taylor, I always feel I should genuflect when I mention Joe Taylor, but I won't. For out to 1,600 kilometres on 2 metres, Joe reckons a 10 to 12 element Yagi is close to optimum. Hasn't got too much gain. If you make it too gainy, this pattern comes down, and you end up illuminating a small area. Whereas with meteor scatter, remember, these trails are all over the place. You want a relatively wide beam width, if you can get it, wide beam width and high gain, right? So a 10 to 12 element Yagi is probably optimum for 2 meter MS, but a vertical stack of 2 is probably better because you've got a slightly lower vertical beam width. It's a little bit too wide vertically, I'm saying, as a single one, but it does need to be high and in the clear, because if it's close to ground, all sorts of horrible things happen. The main lobe gets tilted up, the side lobes pick up ground noise, pick up houses, noises and all sorts. If you just want to work short paths, you actually want something with quite a wide H-plane beam width. And you can actually get some quite good results if you've got a reasonably quiet site with a horizontal dipole. But you have to have a quiet site, because the problem with a horizontal dipole is it receives everything from everywhere. One of the things I've tried, and my research was actually looking into this, you can actually point your antenna vertically upwards and work things. I've worked Belgium on 6 meter meteor scatter just by doing that. So you suddenly find you get all these 400 kilometer paths and less. And if you do the maths, which as I spent 6 years doing, what you find is you get actually a slight increase in signal amplitude, but the duration goes right down. But think of this zenith point in an antenna. Most meteor burst systems are point to point. But if you can illuminate vertically upwards from your transmitting station, you can actually do omnidirectional. But you have to think a bit carefully about the polarizations when you're doing that. And that's known as endpoint reflection. But one thing to remember on 50 megahertz is generally your antenna will be low. Is BCG here? No, it's not. I'm going to run out of time. Sorry. Let's move on. System receive performance is defined by signal to noise ratio. The signal power depends on the path loss, which we've derived, and the noise power is the added noise from your receiver plus anything the antenna picks up. So what you've got is if your antenna is in a noisy environment, you're going to suffer. if your antenna's got bad side lobes, you're going to suffer. And just a quick calculation here. When your antenna's pointed at the sky, you see a temperature of approximately 350 Kelvin. And this bad DX antenna again, what this slide was meant to show was all these noise things add together. So you've got all the stuff in the transmission lines, amplifiers, components, sky background, ionospheric noise, earth and ground noise, radio stars, the sun noise, the atmosphere, and then you've got all this. Then you've got this man-made noise. So all those things add together to make your sight horrible. And if you look at this plot, which was done in 2008, the level there is thermal noise. If you go to 2 meters, even looking at the sky, you've got about plus 8 to 10 dB of noise. But when you go up into an urban environment, you probably into your 30 dB above thermal. What that means is if you're running a watt, the other station's got to run a megawatt. No, a kilowatt, sorry. Sorry, I lost the power. So noise is a really important thing. So, and you can very easily go from 300 or 350 Kelvin. Just walk on if you want me to finish. I'll shut up or I'll keep going.
When it comes to it.
Okay, I'm going to have to stop because I've run out of time. Sorry.
What I was thinking is if anybody wanted to go to the next talk, I want to stay here, we could do questions for a few minutes.
Yeah, okay. Basically, the point I was trying to make is sites are noisy, but I've run out of time. My apologies.
I mean, to be honest, John,
Anybody hasn't heard a meteor ping for the very first time, and I guess there might be quite a few in the room. In radio, it's probably one of the finest things you'll ever hear. Your first one. I remember I was still at school. I rigged this thing up, and with my first EME QSO, it kind of rivaled that. And once you get into it, the interest is absolutely fantastic. John mentioned the video by Lynn, GWAJLY. If you've never done it, Google Meteor Scatter for Beginners, and and just watch the video. It really is excellent. Anyway, any questions?
Will allow me a couple of minutes for questions because he's next.
Because I'm not due to hop. Overlaps with other streams
Well,
of the problem.
okay. Well, if anybody wants to go to another talk, my apologies. And if you want me to finish, because I have a few points that do overlap quite well with this is where you find out how popular you've been.
You're popular, I'm unpopular. Right.
Okay, so what I was going to say. Sorry. What I was going to say is you can very easily have a 10 or a 20 dB noise floor above a perfectly quiet place, and that can cripple these systems because all your thresholds go up. And the other thing, there's a point that John pointed out to me about 2 days ago, which I thought was really interesting. Every radio path has what's known as a Fresnel zone, which is if you block any of that path, any of that Fresnel zone, like with a tree, even though it's above the line of sight, you actually get some blocking in that situation. Okay, and the same applies to receiving. So if you've got any noise sources in that, especially in that first Fresnel zone, you will pick them up. Your antenna is going to pick them up, and this is the interesting thing. And if you actually there's a nice flat Earth. Actually, that's what the situation is, greatly exaggerated. And with a meteor burst path, you might actually be doing that sort of thing. Okay, so if you've got a city there and you're in the middle of nowhere, that'll be outside your first Fresnel zone because it's going way up here. So you think, right, I will raise my antennas then. Suddenly you can see that distant noise source. So it's not always the best thing to do is to have your antennas too high. And John's given me examples of his in the wilds of Suffolk. So that's really all I wanted to say. And this is the one that this is the slide that always makes me weep. This is a plot of noise against as I take my antenna around from north. There's my quietest spot there. And just to put that in perspective, that's about 10 dB above thermal, something like that. When I rotate my antenna at home, this is 1 dB per division. I've got a noise source that's 1, 2, 3, 4, 5, 6, 7, 8 dB above that. And then it goes down to a nice quiet situation, and then back up the other side. And do you notice, it doesn't matter which end of the beam's pointing at that noise source, it's still exactly the same level, because it's got all these horrible side lobes on it. And then you eventually go back, and eventually you're back to here again. But the only saving grace for my site is that southeast. So that gets me into Europe. Okay, so that's it really. And if anybody has any questions, just a quick summary. Oops. You've got to know your real elevation angle and use it to your advantage depending on the path length. Antenna gain isn't everything. Sometimes a lower gain, high, wide H-plane is good for short paths. Measure your sight noise. If I could say this to every 2 meter and 70 cm operator, I guarantee you do not know what your sight noise is, but it's dead easy. Next time you have your antennas down, terminate your preamp in a 50 ohm load and look at the noise power coming out of your receiver with the AGC off. When you put your antennas back up, don't forget to disconnect the dummy load, and then compare it with the antennas. And you will be horrified how much that signal rises. And in terms of measuring power, you can do it with WSJT's screens, or you can do it with something like I had there, which is an SDR. But you will be amazed how noisy your site is. And the number of people you hear saying, "Why couldn't you hear me?" And the number of people are running 100 watts from quiet sites, and they're going, "What do you mean you can't hear me? I'm running 100 watts." And it's down to people's sight noise. My sight noise over the last 25 years has gone up by about 15 dB. It's scary. So, right, I'll stop now. Just a couple of people who inspired me. Thank you. I've overdone it.